Okay, good afternoon. Are we all fully fueled on carbs, ready for the afternoon session? Very awake? Okay, today I am going to try to explain monads. So to start off, who here knows what monads are? Just by show of hands. Okay. Who's read about monads, read the computer science, and has no clue what it's actually trying to say? Okay, it makes sense. Okay, so before I get started, I'd like somebody to tell me what this does, this command. It's pretty straightforward, actually. Yep, it's exactly what it does. So this is a Unix command which basically looks for all of the running Java processes on your machine and kills them. Living large, hey? Living on the edge. Okay. The way this works basically is you've got your ps minus ef, which gives you a list of all your processes together with the command. This then pipes to grep Java, which filters out any of the processes that have Java in the name, so it'll pick up your Java executable. The tr minus s space basically takes the input string and then transforms all the white spaces, things like tabs, non-printables, etc., and then replaces them with a space. Now that I've got a standardized string that's basically delimited by spaces, I can call the cut command and I can extract the process ID from that incoming string. The last little thing I have to do is then call xargs, and xargs is a very useful little Unix tool which basically you can give it a command, and whatever input you have from system in, it'll append it to that command and then run that command. Okay, so this way of programming it's almost seen as like a golden standard for how you should be able to build very composable, decoupled processes, linking them together. And we'll come back to this a little bit later. Okay, so my name's Julian Exenberger. I'm an architect developer for Capgemini. I use a slash because I'm a consultant, so whatever the client needs me to do, I will play that role. I've been in Java development since 2000, so back when things like applets were cool. Anybody remember those? Sun was still a thing, and I think in 2000 they still actually turned a profit. My favorite IDE at the time was a thing called Ball J Builder. So if you still remember what that is, then you're really old school. My first exposure to functional programming and monads was in 2006. This is outside of studies and university and so forth. However, I only actually figured out the monads, and Haskell is quite famous for its use of monads. I actually only figured out how that all fits together much, much later. Okay, so I need to take you through a little bit of functional programming background, right? So I'm going to try to avoid a lot of computer science jargon and try to explain this as simply as I understand it. So if you want to argue about me, about some computer science, please come afterwards and we can debate. It's normally fun debates as well, so I look forward to it. But I need to take you through a little bit of functional programming background. Okay, so what is functional programming? In about the mid-2000s, there was a rise of new programming paradigms, languages like Ruby, and at the time also the Link framework in C# was coming out. And people realized, hey, you know what? All these languages have got these cool new features, and you can't do it in Java. And suddenly, because of that, functional programming became a thing. And of course, everybody at the time, and this is the mid-2000s, once again declared Java dead. And that was about 17 years ago now. Jokes aside, functional programming is effectively a declarative approach to programming where you construct programs from composing and evaluating functions. The evaluating piece is quite important. Everything in a functional programming language is effectively an expression, and that expression gets evaluated to a result. What you're effectively doing is building trees of these expressions that call functions, and you apply a set of values, and values is important. Values implies immutability. A value is fixed, so once you create a value, it cannot change. And you apply this value to those expressions, the tree of expressions, to transform it into a desired result. Best example of this is Lisp. Lisp is effectively a wrapper around your AST, or abstract syntax tree. And in Lisp, you push a list of values through this structure to get a desired result. This is opposed to imperative programming. So all of our most popular programming languages, including Java, of course, are imperative. An imperative programming language, the way that you achieve a desired result with your program is you have a variable which points to somewhere in memory. You then apply a sequence of statements to that variable, and that effectively, you use those statements to modify that memory to get your result. Very simple example of this in action is incrementing values in an array. So there we have int list, which is an integer array. We loop over that integer array, and then we increment each value. We've effectively mutated the state of int list to do that. This is a more functional approach, so I'm pretty sure you would all be familiar with this. I create a new list. I call the stream on the list, and I apply a function to it. So I declare that for each element of this list, I apply a function via the map method, and then I extract it into toList, which then streams the value of int list, maps it to the function, and returns me new list. Important thing to note is that int list and new list are not the same object, right? So I've effectively created a new list, and I've transformed the values in the old list into the new list. One of the goals of functional programming is this idea of referential transparency. There's a programming optimization technique called memoization. I dare you all to say that after a couple of beers. And memoization basically says that if I call a method or a function with the same set of parameters, I should be able to cache the result, and the next time that method or function is called with the same set of parameters, I should be able to return the result. So if I have a function that adds two values together, and if I pass 1 plus 1, the first time I compute it to add 1 to 1 giving 2, but the next time that function or method is called with 1 plus 1 as a parameter, I should be able to safely return the value of 2 without actually having to recompute it. This is something that is possible in a functional programming languages, provided, of course, that you're working statelessly. And what I mean by that is you don't have any state, you don't have any variables that you're actually modifying inside your functions which have potential side effects. And of course, if you don't have a lot of side effects in your code, this means that it's less error prone. You can do things like run things concurrently, and this is really the thing that makes functional programming such an attractive thing, although it's mainly stayed in academia for the most part. Now, you don't get this for free, right? A functional programming language has to have a certain amount of features in it that supports this type of programming. So we already talked about the fact that you have values, and values are immutable. But certainly, you need to have functions as high-order types within your programming language. All right, so they need to be first class, i.e., they can be referenced as a variable or a type. They need to be a high order, so I can pass them as a parameter to a function. And finally, I should be able to create anonymous functions or inline functions, or as we would generally know them, lambdas. What this means in practice is that in a functional programming language, functions are first-class types. So in the same way that in Java you've got OO languages, in class you've got classes, in OO languages, in functions you can reference your functions as an actual type. So it's got a shape. Normally the shape is the combination of parameters and its return type. And you can reference this type as you would any other type in your system, just as you would reference a class or an integer or any of those things in your type system. Now, you think, well, Java is an imperative programming language, but the nice thing about a lot of these functional features is that they actually do translate into an imperative language like Java. So, of course, in Java, we're able to support this since Java 8 with the use of SAM interfaces. SAM stands for Single Access Method. Hands up, anybody who actually knew what that means? Okay. And effectively, what that does is it gives you the Lambda syntax, and it transforms that into an actual function type. Now you can reference that function type, in my case, adder. You can reference it as if you would reference any other interface in your programming language. You can pass it as a parameter. You can return it, etc., etc. Okay, so that's a brief introduction to functional programming. Now, let's talk a little bit about monads. If you do a search on the internet and you ask, what is a monad? You are going to get this response. A monad is a monoid, say that one this late in the afternoon, in the category of endofunctors. So who here knows what that actually means? Okay. I know about 80% of this. So there's a whole lot of theory that you need to actually cover just to get to this statement. Okay, and what's happened in the community is the concept of monads have become shrouded in this whole computer science thing, and now we talk about it, and people don't know what it is. What it actually is a data structure. Okay, it's a data structure that you have a value and you can apply a function to that value. And that function returns a new instance of that monad with the result of that function that you apply to it. Okay, in order for this to be a monad, you need to have a couple of components which make it up. Okay, so you've got what's called the unit function, or the constructor. So in our example, I've got a class monad, and my unit function, which creates the monad, is a simple constructor which takes a value of type t. You also have a bind function. And in our case, that is called flatMap. And flatMap basically takes whatever value you've stored inside your monad, applies a function to that, which takes the result of that function and wraps that result in a new monad. And then finally, you have a yield function, or the get. Very simple. Now you've created this monad, you've maybe transformed it, now you want to extract the value out of it. I call get, and that simply returns the value. The one thing I want to mention about this is that, and you'll often see this when you're working with different types of monads, if you've got a map function. And for the purposes of this talk, map is very simple, very simply a convenience version of flatMap, where it does the wrapping of the results of what you've transferred into a new monad for you. Okay, and very often I'll use flatMap and map kind of interchangeably, just so that you actually know what it is. Does that make sense? Show of hands. Awesome. Okay. Because that's a gnarly little bit of information. Now I'll go on to the next bit of gnarly information. Okay, how would you use this? So This is an example of the monad in action. So I've got a monad of 100, which is a string. I call the map on it, which transforms that string into an integer. I then take the result of that, which of course is a monad, and I apply another map function, which subtracts one value from it, which returns another monad. And then finally, I call toString on that object, which returns another monad, which then takes the result of that and converts it back into a string. So I start out with 100, a string of 100, and I end up with instance B, which is string of 99. Okay. For it to be a monad, it has to adhere to the monadic laws. Okay. The first law, there's three of them. The first law is what's called the left identity law. The left identity law simply says that if I apply a function to a value, it should have the same result as if I create a monad instance of that value and apply the function to it. So an example I have here, I've got add1 as my function. So it literally does that. It adds 1 to whatever value is inside the monad. And I call that function without pushing it through a monad. It gives me 101. And in the second assert equals, I create the monad with a value, call flat map. Oh, there's a mistake in there. But anyway, that should be add1 and then returns the value, and that will be the same. Second law, right identity law. Okay. This is very simple. It simply says that if I were to create a new monad inside my flat map without doing any transformation, the result would be the same as if I had just created the monad directly. Okay, so you can see here I've got monad A, which calls flat map, creates a new instance of that monad for A, and then for B, I simply create that monad of 100, and then they got the same result. The final rule is the associativity rule. So the associativity rule simply says that I should be able to nest a set of functions and get the same result as if I had passed those functions sequentially to my flat map function. And as I said, you'd get the same result. So in my case, I've got function 1 and function 2. The first one adds a value of 1 to 100, and second one, 102. Okay, and what I do there is I call function 1 and function 2 in my monad, so I call flat map on there. And the second one, I call function 1, take the result and apply to function 2. Okay, so in the second call, I nested, yeah? Yeah, I was hoping nobody would notice, but at least I know you're awake. Now, this is what happens when you drink too much coffee just before your talk. Okay, so what is the purpose of all of these rules? These rules basically guarantee that the operation of your monad is inviolable. Okay, so effectively what you're saying is that when I call flat map, I'm always going to get a new monad. So my original monad that I created remains unchanged. Second of all, I'm able to apply a function safely to that, and the state of the monad is not going to be changed. And finally, I can chain a set of functions together, call a flat map together, and get the same result as if I just manually called those functions. Right? So I can rely that I'm going to get the right result of my monadic computation. So what do we have? Essentially, a monad is a data structure that you can chain a set of functions together and pipe a value through that chain of functions. So if you saw in the beginning, I used the example of a Unix pipe. And that's very much a good analogy of how a monad should work, is you create a data structure which wraps a value, you chain a bunch of functions together, and then you can actually push a value through that and do a very complex set of transformations through that in a very extensible way. Okay, so why bother? Why not just call the code manually, right? Why do we have to create this whole fancy data structure for doing what essentially we can already do using normal codes? We can even use standard functions and apply it that way. And yeah, what is the purpose? And the best way I can explain this is to look at some examples. Okay, so the first example is the optional monad from the JDK. Now, I just want to put this in inverted commas, right? The optional that you get with Java is not a pure monad. It has some methods on it that break the monadic rules. Okay, now to the credit of Oracle, they don't actually say that optional is a monad. They don't try to sell it as such. But the optional that we get from Java still has very monadic type of behavior. So I'm guessing everybody's used it. Has anybody not used it? Okay. Question. Of the first time you used optional, did you use optional is present to check whether or not there was a value set? And come on, you can confess, seriously. Okay, that's actually not how you're supposed to use it, right? You're supposed to use it as a pipeline. So in my example, I've got current time millis. I check whether or not at that point in time it's even. If it is even, I return an A, I also return a null. So it simply says, optional simply says that you have a value which may or may not be present. It's optionally present. Whatever the result of that is, I call map. Map will only get called if there is actually something present inside the optional. And then finally, I've got the ability to, if it is null, I can do get or else, and then return some type of default value that I would want to get if this is null. Okay, so this monad has basically given us a very powerful way in how we can do null processing in Java. So if you think, for example, what we would have had to do in something like Spring Boot repositories is historically you'd create a finder method, and that finder method could return null. Or you create a deo method which returns null. And you'd have to actually check whether or not that value is null with any potential null pointer exceptions. And there's nothing that actually tells you, unless you know what the method is doing, that that would have returned null. So here you have an example of a monad allowing you to do powerful processing on certain types of state. Then the other one that's quite common is the stream monad. So a stream is basically a sequence of potentially unbounded items. That could be a collection, it could be an array, it could be a single value if you wanted to. I've written some code, for example, to wrap a result set from a database as a stream. And I can then take the stream as an abstraction, and I can apply a set of transformational, declarative transformational computations on the items that are coming from the stream. Okay, so in my example here, I basically have a list of string integers, convert them to integers, filter them out if they're not even, and then convert them to doubles, and finally I extracted my yield function. In this case is a toList. This is as opposed to how we would have had to do it before Java 8. So, like I said, you can still do the same thing, but now I have to actually create an instance of a new list that I want to populate. I have to do some selection structure, I've got to do some iteration, and I'm sure you'll agree with me that it's actually a lot easier to read a stream than it is to read this type of code to figure out what it's doing. Okay, so that's something you get with the JDK. What about things that we don't have inside the JDK? Best way to explain this is to walk through an example. So this is some very, very, very naive service code. Okay, so you've got some type of service, maybe inside Spring Boot or something like that, and you want to save a customer. You've got a repository of some kind, which is basically going to do the physical saving of the customer that you inject into your service. You have a save method which takes the customer, you save it, you get back an ID, set the ID on the customer. Okay, very basic, very simple, not very useful. Okay, why is that? Because generally, in the real world, we have to do some processing on our customer before it. So here we have some very, very naive validation. We check whether or not the name is actually set, if it's null or not, and then throw an exception. You can get fancy, you can have, for example, a validation exception of some type. I have seen code like this. And again, it only really works for very simple cases. Normally, it starts getting hairy quite quickly, because if you think something like customer, if you work for something like a bank, a customer can have 100+ fields, and you need to validate all of them. And on top of that, you need to do complex validations on different fields within your customer. So you could go and throw an exception every time you have some value that doesn't meet the criteria. It's not great, and generally from a user experience, you want to be able to validate that customer and return all of the errors that this customer has wrong with it. So this type of code is not going to scale. You can use a pattern. I've seen this a lot inside RPC calls, RPC-style code, where you're doing a lot of remote stuff. You use the request-response pattern, where you encapsulate your whole operation into a set of objects. So in our case, we've got save customer request, which simply carries the customer payload. You have a save customer response, and the save customer response basically encapsulates whether or not this operation to save the customer was successful. If it wasn't successful, it's got a list of error validation messages that you can interrogate to understand why it failed. Or if it's successful, you simply pass back the customer, and you can encapsulate whether or not this is a success with methods inside your save customer response. Okay, anybody used this pattern before? Okay. However, is there a monad that you can use which maps this state? Okay, so you've got this scenario where you're calling a method, and either you have success or you have failure. You could use the either monad. So the either monad is basically a monad says that you can have one of two possible values. A left, or typically it's called a left or a right value. Okay, so I'm going to make a call to a method, and I'm going to get back an either monad. Either could either contain some value or another value. And typically we would use this where we want to represent an operation which can have a success outcome, or it can have a failure outcome. And typically what we do is we have left and right maps to a successful result, and left generally reflects a failure. So in my example, I have save customer. I've got an either which either will return the customer if it's success, or it will return a list of errors if it's a failure. Okay. Sorry? Yeah. Man, it's been one of those days. Really been one of those days. Hey? Sorry? If your name is no, the second is no. Yeah. Yep. Like I said, one of those days. At least, you know what? At least I know you're awake, which is a good sign. Which either you're like finding something to nail me on, which is also a possibility, or you're actually awake and interested. So either way, at least you're awake. Okay, whatever the case may be, if the error list is empty, then I return right, which means it's a success, or it's left if it's a failure. And when I consume it, I can process it appropriately in the same way I might process something like an optional. So I've got an either, which if right is set, so it's a successful outcome, I can then take that value, and this is a typical example of what you might have in Spring Boot. I take that value, I do a HTTP 201 created, generate a URI from that, and then pass back the customer as the body. Or if it's a failure, I do a 400, and map left takes the left-hand side, so in this case, the body will become the error list. And then I've got the as method, which is a yield, and that does a narrowing and takes that value and narrows it into a single type. Okay, so that's quite a readable, I'm sure you'll agree with me, that's quite a readable way of doing things. It beats having to do a whole bunch of ifs. And certainly, one of the benefits that I've seen when I've worked with monads is that if I create this as a standard way of processing layers inside my application, I can kind of bubble up my either, right? So I can bubble up, I can have a service which returns an either monad that bubbles up. I might do some error transformation, or if I have standard error structures, I can kind of just push that up into my layers. I don't have to do any intermediate error processing. Okay, so as I said before, monads are just a data structure. If you can think of something that follows the components of a monad, and if it obeys the monad laws, then it is a monad. So there are yet unwritten monads that are floating around out there that you'll be able to write. And there's a couple of monads which I haven't covered. Result is basically just a specialization of either. Okay, so that makes it a little bit more explicit, where you have your left and right is specified as okay and error, or okay and failure, for example. So that's a little bit clearer than if you just use the either straight up. You've got the try monad. A try monad wraps a try catch exception. Okay, so what this will do is either you will return a successful monad, a successful result with your try, or you can catch an exception and then it'll return as the error state, it'll return that exception. You also have something like promises from JavaScript, which is also a type of monad. And this allows you to handle asynchronous coding in quite a nice way. Okay, so coming back to our original thing, what monads effectively allow us to do is to take the Unix programming model, this kind of gold standard for programming of being able to take simple functions which do one thing and chain them together and bring them into our standard programming language. And that's really what you get if you use monads. This ability to have a data structure which wraps some type of value that you can arbitrarily chain a whole bunch of computations to it and then run a value through that computation. Questions? Silence. Okay, so before I close, yeah.
Do you see this one monad as an addition to Java, or do you encourage people to write their own monads? Because I think other than these that we have, the optional, the stream, the either, do you see more new monads, or do you just say use this one monad more?
Look, I mean, what I've shown you is just basically the most common monads, okay, where people have been able to find uses for them. All right. You need to use what works in your environment, and generally, like the monads that I've shown will cover about 90% of the cases that we can really see it's useful. Okay, but I mean that doesn't preclude identifying something new. I don't know if that answers your question. Yeah.
I think, does it deserve to be something magical monad if it's optional stream or either? Does it really?
No, I don't think so.
Yeah.
No, I mean I think you like I said, I mean use the standard stuff and you'll be covered for 90%, 99%. Yeah.
Is it possible to compose monads? So is it possible to compose an either with a try?
Well, I mean, a try kind of is a specialization of either. Do you mean in terms of? It depends. In Java, the way I'd see it is based on your operations. I mean, remember, Java is kind of limited in what it can do. But I mean, if you think of something like stream, you apply a function and that might return an optional. I don't know if that makes sense. We can't create these like fancy combinations of functions like you might do in Kotlin or Scala or something like that. Of course, you've got the ability in your actual functions, your actual Lambda functions, you can actually do composition there. Again, I don't know if that answers your question. Yeah. Okay. Book I highly recommend is Structure and Interpretation of Computer Programs. This is quite an old book now, but it is still kind of the gold standard for if you want to learn a little bit more about functional programming. You can probably get it floating around the internet as an ebook quite easily. For me, it was worth getting the hard copy of this. And then if you want to get a functional programming library for Java, there's Vavr. I don't know if it's VAVR or just vavr.io. This, together with a whole bunch of other things, also has all the monads that I've described now. So you don't have to write them yourself. You can just kind of get this library and then work with it. It's not the only library for Java, but it is one of the most popular ones. Okay. So if you want to connect with me, please feel free to do so. This is a link to my LinkedIn page. I do also write some articles, mostly anecdotal stuff from 23 odd years in the programming world. So yeah, please feel free to connect and read my content, and I'll read yours. Thank you very much. I hope you all understand monads now. And yeah, thank you.